Good morning, everyone. I am Pushpita Majumdar, PhD student at AAAI Delhi, India, and today I am here to present my research work on learning deep models with imbalanced data distribution. Machine learning and deep learning algorithms have achieved tremendous success, and significant advancements are made in various applications such as facial analytic tasks, including face recognition and attribute prediction. However, the performance of these algorithms depends significantly on the training data distribution, and an imbalance leads to degradation in model performance. Imbalance in training data could be in a subclass within a class or in a particular class or sets of classes. Real-world problems such as injured image recognition is an example of imbalanced subclass distribution. For recognition of an injured victim, both injured and non-injured samples are required. Generally, the number of injured samples are lesser than the number of non-injured samples, which in turn results in imbalanced subclass distribution. Other real-world problems such as altered image detection is an example of imbalanced class distribution. Here, altered or fake images constitute a small portion of the training data compared to the original images. Recently reported bias in model prediction is also an adverse effect of imbalanced data distribution. So my research focuses on designing and developing solutions for different real-world problems with imbalanced data distribution, primarily focusing on facial analysis problems. In this regard, I have introduced the problem of injured face recognition. Injuries are common in road accidents, violence, and natural disasters. Every year, 1.25 million people are killed and 50 million people are injured in road accidents. 50 to 70% of people surviving traffic accidents have facial injuries. Thus, injured face recognition is required to identify the victims of road accidents, natural disasters, or they could be used to recover the identities of unidentified dead bodies. So, in this research, we have first created a dataset of injured and non-injured images by downloading images from the internet of 150 subjects. This is the first work towards this direction, and thus there was no publicly available dataset. So our first step was to create the dataset or the injured face database. After this, we have evaluated the performance of existing face recognition algorithm on this database, and we have observed that existing algorithms do not perform well for the task of injured face recognition. To further analyze our observation, we have observed the TSNE visualization, and it is found that when injured images are given along with non-injured images as an input to the model, the overlap increases in feature space, which in turn degrades the overall model performance. Thus, in this research, we have considered injured and non-injured images as two different subclasses and introduced a new space which we have termed as subclass space, where the scores computed using the feature representation of injured and non-injured subclasses are optimized. Further, we have proposed a novel loss function termed as subclass injured face identification loss that optimizes the scores in subclass space such that the overlap among the samples of different subjects is reduced in the feature space. This is the block diagram of the training process of a model using the proposed sci-fi laws. As I have mentioned that in this research we have considered injured and non-injured images as two different subclasses. So the first task is to generate a three-tuple by taking two samples from the non-injured subclass and one from the injured subclass. This three-tuple is then given as an input to a face recognition model to obtain its corresponding feature representation. After this, subclass scores are computed by taking the Euclidean distance between the feature representations and they are projected to the subclass space. In the subclass space, the loss is computed to update the model. This process is repeated until convergence. We have compared our proposed loss function with existing state-of-the-art loss functions, and it is observed that the proposed loss function performs best by increasing the classification accuracy approximately by 3% from the best existing loss function, best performing existing loss function. In the next problems that I have dealt with is altered image detection. So this is again a problem of imbalanced class distribution. So here we have proposed a network to detect partially tampered faces. At first, partially tempered faces are generated by replacement and morphing of facial regions. Next, the performance of face recognition models are evaluated on the tempered faces, and it is observed that the recognition performance degrades significantly when the tempered images are given as input. Therefore, we have proposed this partial face tampering detection network to detect the altered images. This network takes RGB and high-pass filter version of the input image as an input to detect the altered images. The proposed network achieves more than 90% accuracy for partial tempered face detection. Next work is to detect synthetically generated images specifically using GANs and retouching and distinguishing these synthetically generated images from original ones. So for this we first generated synthetic images using different models of GANs, and we took retouched images from the ND-IIIT retouching face dataset, and we have taken CMU original images from the CMU multiply dataset. So for this we have trained a three-level hierarchical network where the first level distinguishes the original images from the altered ones. The second level further distinguishes the altered images into retouched and GAN-generated images. And the third level detects the GAN models used to generate the synthetic images. During training of this model, the level 1 is trained first with original and altered images. After this, level 2 is trained using retouched and GAN-generated images, and the weights of the first level are frozen. During training of level 3, level 1 and level 2 weights are kept frozen. The proposed network achieves more than 99% accuracy for altered image detection. Recently, the research community is moving towards designing and developing fair models that produce unbiased outcomes. So, bias prediction is also an adverse effect of imbalanced data distribution with respect to some demographic subgroups. Therefore, designing mechanisms to improve the trustability and dependability of these systems is of paramount importance. However, there is always a trade-off between fairness and model performance. Removal of bias may affect the overall model performance, while a high-performing model may affect the performance of the underrepresented subgroup. Therefore, it is important to measure the trade-off between bias and model performance through a unified metric and to mitigate the effect of bias without affecting the model performance. Existing fairness evaluation metric they do not consider the overall model performance. On the other hand, performance evaluation metric they do not consider the bias in model prediction. Therefore, it is very important to uh, have a metric that provides a joint estimate of both. Therefore, in this research, we propose a unified metric which we have termed as precise subgroup equivalence that provides a joint estimate of bias in model prediction and the overall model performance. Next, we propose a novel algorithm based on adversarial perturbation for bias mitigation that utilizes the model prediction to learn a single uniform subgroup invariant perturbation for a given dataset. This is the first time that adversarial perturbation is used for bias mitigation. The learned perturbation is added to the input dataset to generate a transformed dataset. The transformed dataset, when given as an input to the pre-trained model, generates unbiased predictions. This is the block diagram of the steps involved in learning the subgroup invariant perturbation. So in the first step, SIP n is initialized with zeros and is added to the input images to generate a transformed dataset. This transformed dataset is given as an input to a pre-trained model to obtain its output prediction of the probabilities. After this, loss is computed and optimization is performed over the perturbation n. This process is repeated until convergence. We have compared our proposed algorithm with existing bias mitigation algorithms, and we have found that the proposed algorithm achieves lowest PAC compared to the existing algorithms. We have also compared our proposed loss function by alternatively optimizing bias and overall model performance alternatively using our proposed algorithm. And it is found that the proposed loss function further reduces the bias in model prediction. Currently, I am extending this work to learn a single perturbation for mitigating the effect of bias from multiple demographic subgroups. Also, I am developing different algorithms for mitigating bias in face recognition. Thank you everyone. If you have any questions, feel free to let me know. Thank you.